analog circuit, we are going to discuss about differential amplifiers. So before solving some problems under differential amplifiers, let me start introduction. So you know what is differential amplifier, right? So differential amplifier is nothing but it's going to amplify the difference of two signals. Okay. So this is the basic diagram for a differential amplifier. So in the differential amplifier, we have a two input voltage, that is V1 and V2. The difference of the voltage is going to amplify and going to give a output V0. So what is VD here? VD is nothing but difference of these two voltage V1 and V2. So this is a diagram for differential amplifier. This differential amplifier, we are in here, this diagram, there are two input voltage, that is V1 and V2, right? So these difference V1, that is V1 minus V2 difference voltage, we are going to give for this differential amplifier input. So for this diagram, we require two transistors for giving two inputs, Q1 and Q2, that is BJT transistor, NPN type. So here the input resistance is connected in the base of Q1 and input resistance, that is source resistance RS, is connected at the base of Q2. Okay, so here for the transistor Q1, we are feeding a input VS1, and here we are feeding a VS2 input. Okay, so for this transistor, for getting biased circuit, we are giving external DC supply, that is plus VCC. Okay, so this is your RC resistance, where we are going to take this output for differential amplifier means from two terminals, that is Q1 collector point, that is C1, and Q2, that is C2 node, that is a transistor Q2 collector point. So the required output is nothing but V0 is equal to, what is your required output? So this is your differential amplifier. So differences of input is given to the transistor, and corresponding output we are getting at the output side V0. So this differential amplifier is going to work in two different mode. That is, one is common mode, another one is differential mode. Okay, so here this common area, that is the emitter, both transistor Q1 and Q2 transistor emitter is connected with the resistor RE. Here the negative basis of biasing we are feeding here, that is the value of minus VEE. Okay, so I told you, know, this is your differential amplifier. So that output is nothing but V0 is equal to, that is directly proportional with your differences of two input. The differences of two input is nothing but V1 minus V2. These V1 and V2 is nothing but your input. We are feeding at the base of transistor 1 and the base of transistor 2. So the first mode of operation is a differential mode of operation. In differential mode, we are going to calculate what is the value of differential gain. Okay, the differential gain is nothing but AD value. So V0, that proportionality constant is given here as a AD. The AD is nothing but a constant value. That value is nothing but a differential gain. Gain is nothing but output divided by input. So what is your output? The output we are getting from the collector, C1 collector and C2 collector of transistor Q1 and Q2. This is your output. So output is equal to proportionality gain AD into V1 minus V2. So AD is equal to, so what is your value we are getting from here? V0 is equal, that is AD is equal to V0 divided by VD. VD is nothing but differences of two voltage. So this can be, we can simplify and write like GM. What is this GM? GM is nothing but trans conductance, GM into resistance on the collector side, that is RC. Okay, and the next mode of operation is nothing but common mode operation. Here we are going to calculate a common mode gain. So common mode gain, that is differential mode gain, is specified as A in suffix C. Common mode gain, we are representing this value as AD. Okay, in common mode, common means that is two inputs are added. Difference of two input giving means that is called as differential mode operation. Common mode means to addition of two inputs. Addition of two inputs means that is your value of average value, that is V1 plus V2 divided by 2. That is your two input voltage. Okay, so that is given here for a common mode gain. So that V0 is equal to that proportionality constant, here it's mentioned as a AC, because it is a common mode, AC into VC. So from that we can calculate what is the value of AC. Okay, so for AC, what is your value with respect to a resistor means minus RC divided by RE. But in the case of differential mode, So the value of AD is equal to with the transconductance. So minus GM into RC. So the next is in the differential amplifiers, the main important parameter is a calculation of common mode rejection ratio CMRR. So what we are going to reject here means the ability of the differential amplifier to reject the common mode signal. Okay, so for rejecting a common mode, so this specification is needed, that is CMRR, common mode rejection ratio. So this common mode rejection ratio is nothing but it's an ratio of differential gain AD divided by AC. That is common mode, that is differential voltage gain AD divided by common mode gain AC. So that value is given with respect to a resistor value means GM into RE. See students, here for AD that is minus GM into RC. In the case of CMRR it is plus GM, plus transconductance, that is GM into RE. So overall CMRR value with respect to the or in terms of logarithmic value means we can represent in terms of logarithmic, that is 20 log. Okay, 20 log because it is a gain, right? So 20 log AD divided by AC. So representing in decibel value, so dB. Unit is decibel dB. So what is the value of, what is the equation or what is the formula for input resistance and output resistance in both the mode, differential mode and common mode means, first case we'll discuss differential mode. Differential mode input resistance value is Ri, that is Ri is equal to 2 into emitter resistance, that is Re. Differential mode output resistance value is nothing but R0 is equal to Rc, which parallel with output resistance R0. So this is the diagram for differential amplifier using FET concept. Before we discussed about BJT. So this one is a FET. By using FET, what is your small signal analysis? That is AC cases, the AC analysis and DC analysis we are going to discuss now. So this one is two sets of transistor Q1 and Q2, where Q1 and Q2 are FET. So we have three terminals called drain, source and gate. So for this case, for FET the differential amplifiers, again it is operating under the same similar like BJT, working under two sets of mode, that is common mode and differential mode. So for AD the value was nothing but minus GM into RD, but in BJT we are getting RC now. For collector here it is a drain, so RD resistance, and common mode gain AC is equal to minus RD divided by RS, that is source resistance. Okay, so overall CMRR value is nothing but, you know, the formula is nothing but a ratio of AD divided by AC, so that value is GM into RS. So what are the requirements or what are the assumptions we are doing for analysis means? So consider the two transistors are identical transistor. Identical transistor means all the specifications values are like similar values. We are going to take circuit elements or symmetric above the mid plane. Okay, so identical bias voltage as the Q1 and Q2 gates are nothing but VG1 and VG2, both should be equal. Okay, signal voltages and currents are different because your value of V1 and V2 both are not equal. The next one is here the drain resistance RD. So for this load drain resistance, it is acting as a resistance current mirror and also an active load. And moving to a source resistance RSS, these two sources are connected with a common resistance, so it is mentioned as a RSS. So the RSS values we can specify as a bias resistor or a current source or a current mirror circuit. Here the transistor Q1 and Q2 are in which mode? CS configuration mode. So input at the gate and the output at the drain, but with the source is connected to each other, that is connected with your negative biasing voltage minus VSS. So while doing this analysis case, here this is your drain current ID flowing from here, and this is your ID current. Both the two ID values are joined here through a resistor RS. So total value ID plus ID, two ID value we are getting here. So what happened to your VG value? VG value is nothing but that is nothing but equal to both the transistor gate voltage. So VG1, VG2 is equal to V. Okay, VG. And then source voltage into both the transistor for source voltage VS1, VS2 is equal to VS, and VG1, VGS2 is nothing but VG, or we can also say it as a VGS. So what is your output at the transistor 1 and transistor 2? Output voltage is nothing but V1. So both the values are equal to an output voltage of VOV. Similarly, drain current ID1 and ID2 is equal to a common drain of ID. So likewise, we can also represent this GM1 and GM2 as a GM, and R01 and R02 as R0. Okay. So this is a calculation of differential gain, differential amplifier gain. So we know that VGS is nothing but a voltage across the gate and the source. So this is the value of V1 and V3, differential mode of operation. So both the values are in difference of input voltage we are going to give. So V1 minus V3. So and then VGS2, for VGS2, what is the input? Again, a differences of two voltage like V2 minus V3. So here in the node of V01, that is here. Here, what is the value of output voltage we are getting means V01 divided by RD plus V01, that is V01 minus V3 value divided by R0 plus transconductance GM into V1 minus V3. So likewise, we can calculate V02 and also V3 value. Okay. So now the differential amplifier is in common mode. When it is in a common mode, what are the assumptions and in which way we are going to calculate this output voltage and drain current? Let me see now. So for this, we have to set, this is your assumption of setting voltage of VD is equal to 0, so that V1 value is equal to plus VC, as well as V2 is also a positive value of VC. So V01 is equal to V02, and ID value, that is ID1 and ID2 and ID, both all the three are equal. And again on the common mode case, the calculation for this area, calculation for ID current. So here the ID current, this is the path of ID1, that is this is the path of ID2 from the transistor 2. Both are combined through a resistor, source resistor. So this is your 2ID. That 2ID value is split. This is one node and this is one branch, and this is again another branch. So we are we are dividing this resistor into a two part, that is 2RS and 2RS. Now we are calculating what happened, calculating the value of ID current here. So the ID path, see here, the ID path is from this node. From the node, it is splitting here, and then again it is moving from this part. So ID current is moving towards V3. So this V3 term is dividing into a two branches. Okay. So here it's mentioned, for analysis case, we are breaking this area into two half. So that is called as a half circuit. Okay. See here, because it is both the transistors Q1 and Q2 are a symmetrical case. So if it's symmetrical means it is easy to analyze in one part. That is, we are dividing the circuit into two half. That half part is nothing but an half circuit. Okay, in a common mode, circuit breaks into two identical part, because the transistor Q1 and Q2 we are using in an identical mode. So one case, that is one part, if we analyze, the value is the same for the another identical portion. So by analyzing this in two half, that is half circuit cases, so this is the value of V01 divided by VC or V02. I told you, no, the same value will exist for another symmetrical half. So V01 is equal to V02. Both the values are equal. So that value is equal to. So if you memorize this formula directly, we can use this formula in the problem case. Okay, minus GM into RD divided by 1 plus 2 GM RSS plus RD divided, that is by R0. So next is differential mode of operation. In differential mode, two different sets of voltages we are going to give. So in the differential mode, that is difference of, that is a subtraction of two input voltages. So we are giving V1 as a minus VD divided by 2 and V2 as plus VD divided by 2, and VGS value is equal to, this is your value of VGS for node V01, and this is your value of, by applying a KVL, we are getting this value of V01, V02 and V3. Kirchhoff voltage law we are applying here. So corresponding values we are getting V01, V02 and V3 value. So in this case, V01 is equal to minus V02. Okay. So again here, the same. In differential mode, again, we are doing the same concept. We are breaking down circuit into two half. That is called as identical half circuit. So while splitting this into two halves, you are getting two different form of voltages. But in the case of the common mode, you are getting only one part, that is one voltages, because it is operating under a common mode. It is operating under a differential mode. So we are getting two different values of voltages. So V01 divided by minus 0.5 VD value is this one, and V02, that is positive version of V02, will get this answer. Okay. So this is the concept of it summarized here, both common mode and differential mode in a same slide. It is mentioned. It's a common mode and differential mode, like a half mode circuit. That is a half circuit concept. So the points given here is points to remember that in a in a common mode half circuit, a current about symmetry lines are equal. Voltages about the symmetry line are equal. That is V01 is equal to voltages at both the sides of transistor Q1 and Q2 are equal. No current acrosses the symmetry line. Okay, there is no current across any symmetry line. In a differential mode, these are the points to remember. Current above the symmetry line are equal in values and opposite in sign. But in the case of voltage above the symmetric line are equal in value. Again, same. Current and voltages both are symmetry above the symmetry line are equal in the values and opposite in the sign. Okay, the voltage at the symmetry line is 0 here. So these are all the steps for, these are all actually a procedure, or we can say it as a steps for converting the original basic diagram into half circuit. So that is the constructing half circuit. How to construct this half circuit? It is step by step procedure. Here it is given. Okay, this one we already discussed. See, these are all the steps. This is a step for common mode half circuit. I told you, the common mode, the value of voltages are equal. That is V01 is equal to V02. ID1 is equal to ID2. No current across the symmetry line. In the case of differential mode circuit, current above symmetry line are equal, but they are in opposite sign. Voltage above the symmetry line are equal, but opposite sign. Okay, so we are getting a negative value here. Here in the case, no current across the symmetry line. Here the voltages on the symmetry line is 0. For the case of differential mode half circuit. Whether this half circuit is, you may have this doubt. So everyone, in everyone mind, definitely this question will arise, that half circuit works only if the circuit is in symmetry. Half circuits for common mode and differential mode are different. Okay, bias circuit is similar to half circuit for a common mode. Not all different amplifiers are symmetric. Okay, we should see the load part carefully. Not all different amplifiers are symmetric. Okay, for a perfect symmetry case, if one resistor has RD and another RD value we are getting, means that plus del of RD is nothing but, that is del RD value is very, very less than RD. Why this differential amplifiers are popular? We have so many varieties of amplifiers in an analog circuits. Why specifically this differential amplifiers are popular case, means they are much less sensitive to a noise, because we are calculating here the important factor CMRR, that is common mode rejection ratio. The common mode rejection ratio value is very, very, very less than 1. So, and then the second case is with respect to a biasing, and with in a view of biasing, relatively easy direct coupling of the stages can be required. Biasing resistance RSS does not affect the differential gain, okay, and does not need any bypass capacitor. So in this case, we does not need any type of bypass capacitors in the circuit. No need of precise biasing for a gate or in the part of IC, does not require any precise type of biasing. And DC amplifiers, that is no coupling and no bypass, that is a bypass capacitors are required. Why this large CMRR is more useful? what is the what is the thing here means, a major goal in a circuit design is to minimize the noise level. We have to improvise the signal to noise ratio, that is signal divided by noise ratio means, in the ratio we are going to improvise the signal level and we are going to minimize the value of noise level. So that is noise comes from many sources, it will be coming from many sources. There are so many varieties of sources in a practical case. For noise factor, it may be a thermal or it may be from some example given like electromagnetic waves. So a regular amplifier, that is amplifying. So the amplifier means it will amplify both the signal and as well as a noise. If the noise factor is very high in particular case, practically means the noise level will be high, means what happened to your signal to noise ratio? Signal to noise ratio level will be decreased, that is minimized value we are getting. So in order to improve the noise level to a high range, we are going to reduce the signal to noise ratio. Improvising a signal to noise ratio means we are going to minimize the noise level. So for decreasing or to minimize the noise level, what are the things we are going to consider? So that is the source. So in the source we are getting an output of V1. From that V1 value is given to the amplifier. So that amplifier, that is nothing but a differential amplifier. So that differential amplifier is going to produce the output voltage V0. So V1, what is the value of V1? Definitely the V1 will, it's generating from the source. Obviously, it will have a signal as well as noise. So it's a combination of signal and noise. So what is the value of output? Output is nothing but A into, that is, A is nothing but proportionality constant or a gain. We can say it as a gain. If it is in common mode means AC, a common mode gain. If it is an AD, that is AD means differential gain AD. Okay. So V0 is equal to A into V1 is equal to, which is nothing but that V1 is nothing but, we already discussed that voltage will have definitely a signal and noise. So substitute the value of signal and noise here. Okay. So if the source, this kind of source here, only we are giving one type of source, that is one value of voltage. Here we are giving two voltages, V1 and V2. So both are having a difference value, that is same in voltage but in opposite sign. Okay, same in voltage, same voltage we are providing, zero point 0.5 and 0.5, but in polarity wise they are differ. So V1 is equal to 0.5 the same V signal plus V noise, and V2 is equal to 0.5 V signal plus V noise. So VD, what is the value of VD totally? So V2 minus V1, it's operating in a differential mode. So V2 minus V1 means this is the value of V signal. And what has happened to your VC? VC is nothing but generally a noise signal. So what is the formula for V0? AD into VD plus AC into VC. So while substituting this value, we are getting AD V signal plus AD divided by CMRR into V noise. So these two are comparison of differential amplifier with two identical common source amplifier by perfectly matched circuit. Okay, so by perfectly matched circuit, the two identical, how to connect it, two identical common source amplifier. Comparison of differential amplifier with two identical common source. So this in differential mode of operation. So this is two common source amplifier, and this is a part of half circuit concept, that is two identical circuits are dividing or breaking down here. So that two half circuits, the overall value of, this is your points to remember, overall value of voltages and gain value mentioned here. So these are all the things to memorize. Okay, so this is a differential mode, means this is the same concept with a common mode. In a differential mode, see here, that is a voltage V01, V02 and V0D and differential gain, that is AD, are identical in nature. In the case of common mode, That is V naught 1, that is voltage of a transistor 1 and the voltage of the transistor 2 are different. So the value of common different means it's subtracted. Subtracted means definitely the value will get 0. So V naught, that is VOC is equal to 0. What happened to your CMRR? CMRR value will be definitely it will be an infinite value. Now the comparison of differential amplifier with two identical common source amplifier is summarized here. So the summarized value of AD, these are all the points to remember. These are all the formulas to remember. In a problem solving case, we'll use this formula directly. So in AD is equal to VOD divided by VD is nothing but the value minus GM or not parallel with RD. This is output resistance and this is your drain resistance. AC is equal to VOC divided by VC. That value of AC here we are getting is 0. So CMRR value is equal to infinite value. So in a perfectly matched circuit, there is no difference between differential amplifier and two identical common source amplifiers. So next we are moving on to the part of configurations of differential amplifier. So differential amplifier is working in two sets of mode. One is common mode, another one is a differential mode. And this differential amplifier is working under a configuration. So based on the configuration, we can categorize this one in a 4 level. One is dual input balanced output differential amplifier, dual input unbalanced output differential amplifier, single input balanced output differential amplifier, single input unbalanced output differential amplifier. Out of these 4 configuration, so which one will be most commonly used means the different dual input balanced output is a basic differential amplifier configuration. So instead of even though it has a 4 different levels of configuration, most advantageous and more commonly used in practical case and also theoretical case means dual input balanced output. In order to get a balanced output by feeding a dual input, we can get a respective output from the differential amplifier. So this is the first case of dual input balanced output. Dual input means dual, that is the two different double the value of source is fed at the transistor Q1 and Q2 base B1 and B2. So this is balanced format of input. So that is dual form of input and balanced form of output. Balanced means both the transistor collector C1 and C2 node we are getting the output V0. So the next one is a dual input unbalanced output, a differential amplifier. So in the dual input, again we are feeding a two different sets of input at the VS transistor Q1 and Q2 base, VS1 and VS2. Only one output. One output means it is the symmetrical format of connection, symmetrical form of connection transistor Q1 and Q2. But in the symmetrical format, we are taking only one output from one base of the transistor, any one transistor. So this is your V naught. So it is called as dual input and unbalanced output. Next case is a single input and balanced output. Okay. Even though we are giving a single input, feeding a single input for the transistor Q1, we are getting a balanced format of output from collector of transistor Q1 and Q2. Next one is single input unbalanced output differential amplifier. Here only one input at one side of the transistor and only one output at the collector of same transistor. So these are all the 4 displayed in a one slide. That is 4 for values. That is 4 different diagrams of configuration. That is dual input, balanced output, single input, dual input and unbalanced output. Only one from one side output is taken. Okay. So the next one is one input, that is single input and balanced output, and one single dual. It's not a dual, it's a single input and unbalanced output. So the next next concept in this analog circuit is first one is a differential amplifier, the second one is a current mirror circuit. What do you mean by a current mirror circuit? It is a circuit that output of the current, that is constant current, that is equal to another current. That another current we can consider is that as a reference current. So that reference current, that is current mirror. It's like a mirror images of one particular current. That's why it's called as a current mirror. Generally, a mirror will be a reflection of original version, right? So the same way, here the output current are considered as a constant current. That constant current is equal to a format of another current. That another current we are actually representing as a reference current. So from the diagram, you can easily understand that this is your reference current and this is the output constant current. Okay, this is the output constant current, which is the mirror image, that is mirror of, that we can take it as in a reference current. Here Q1 along with the series resistance determine the reference current. That this is the transistor Q1 and this is the transistor Q2. So from the transistors base, from the transistor base, that is a common connection of transistor Q1 Q2 base is connected with the collector of this transistor. So that current will represent as a reference current. So the transistor that is a collector. This is the collector connected with your voltages. So that current is nothing but the output. That is collector current. That is collector current is nothing but our output current. Q1 along with the series resistance determine the reference current. So this is in the green. Indication is nothing but a reference current, while Q2 is responsible for delivering the output current or mirror current to the load. So this is your mirror current and this is delivered the output current. So this is the equivalent circuit for current mirror circuit. So in the current mirror circuit, so here it is mentioned in a green indication and red indication. That green indication is a reference current and red indication is a collector current, that is an output current. So that is mentioned here along the across the resistor R1 and across the resistor R2. So this is the DC supply here, it's given for a transistor Q1 and a Q2. So here I already told you that a transistor Q1 and Q2 base, that both common connection of base is connected with the collector current. So this is the flow of IC, and here the base current IB1 is flowing towards this direction and this is flowing towards this direction. So from this, what are the things we can analyze means the collector current is given by the equation of IC. So what is here IC? IC is nothing but a basic formula we can write, that is a beta IB. Since the two transistors are in identical nature, what happened to your reference current IRF? IRF is nothing but your IC is flowing in this direction and this 2 IB. Okay, so I reference is equal to, it's nothing but addition of additive of a collector current and two base current value and IC current. So here these two IB is flowing here, and that two IB is dividing into a two path, that is IB1 for transistor 1 and IB2 for a transistor 2. That makes the output current. So what is your overall output current here? Transistor Q2 collector, that is your collector current we mentioned, right? So that is the output current. Since the base current is small compared to a collector current, okay, so base current will be always small than your collector current. So we can assume that the output is always is equal to, see here, see the equation here, the base current 2 IB is very, very small. Small in the case of very less than 1 or very small compared with your IC. So we are neglecting this case. So total output, whatever happened now, it is nothing but your IC means that IC value now it's become only a reference value. So obviously your output current is nothing but your reference current. So from the current mirror circuit, the output current and reference current are equal. So this one is mentioned here in the definition. So from the definition, we can understand that our reference current is equal to our output current. The output current is nothing but our collector current. That collector current is always a constant value of output. So from this, we can understand a current mirror circuit is nothing but reference current. Okay. So now we are moving on to the discussion of gate questions with with this concept of differential amplifier and current mirror circuit. So this is the first question given here. See the diagram. So from the diagram, we can say it is a current mirror circuit. It is here. See, current mirror circuit itself. Circuit means it's a connection of two transistors. Two transistors are should be in identical mode. That is, two transistors are must in identical format. So two transistors base is connected with collector of another transistor Q1. So this is the circuit diagram of current mirror. So the same current mirror circuit we are getting here. So this collector resistance 6 ohm and this is output. We know that output resistance is equal to reference current is equal to output current. When this case will be available? Only when your base current is very, very small. Okay. So you can go through the question and you can start solving. Go through the question and start solving this question. A constant current source using to match the NPN transistor with beta value is equal to 100 and VBE is equal to 0.6 is shown here. Calculate I out. What is your output current I out? What is I out? First, you just recall the concept. I out is equal to what? I reference, right? When it is equal to I reference, when IB is very small. Hmm? So I reference value is what here? First, you mentioned where it is I reference. See, I reference is this one. Imagine the circuit. I reference. So what happened? I is equal to Ohm's law. Apply Ohm's law. V divided by R. Okay. So V means VCC minus VBE. Across I is equal to V by R. Which voltage? It is a that is minus, that is VCC minus VB divided by R. So it is mentioned a VCC value as 12 voltage and VB is nothing but 0.6 voltage is given here. If VBE and VCE value is not mentioned, means you can take a 0.7 value and 0.3 or a 0.3 value you can take. That is VBE value as a 0.7 or 0.3. For silicon and germanium you can take. But in this question, VB is already mentioned here. So 0.6 voltage. Divided by the value of resistance is nothing but a 6K. That R is nothing but VC. Sorry, RC. Resistance across a collector terminal. So 6K. So the value is 1.9 milliamps. What is your final output? The question asked is calculate I out. What is your output current? That is IC, overall IC. IC value formula is beta divided by 2 plus beta I reference. I reference is already calculated here. It is 1.9 milliamps. So that 1.9 milliamps is mentioned here. It is substituted here. So the value is nothing but 1.8 milliamps. So the next question, again the same current mirror circuit. Another type of question. The given data are somewhat different here. The current mirror shown below provided 1.5 milliamps current with supply voltage VCC is 12 voltage. Assume beta is equal to 150 and VBE is equal to 0.7 voltage. Here in the question VB is mentioned. Okay, so what is the value of resistance R1? In the case of previous problem, they asked you to calculate what is the output current I naught, I out, I naught or I out. But here in this case, in this problem, you supposed to calculate the resistance value R1. Okay, again the same formula what we used here is same. I out is equal to beta divided by beta plus 2 into I reference. So what is I reference? What is I reference? The same formula, VCC minus VB divided by the resistance value R. So this R1 is supposed to calculate. So you can put instead of R here R1 at this point. So remaining all the values are in the question. IC value is given as a 1.5 milliamps, means 10 power minus 3 is equal to the beta value is substituted and VCC value is 12 and VB value is mentioned in the question itself 0.7 and you supposed to calculate the R value. So take this R on the left side. So this is the formula and finally you substitute the value. You are getting 7.43 kilo ohms. The next question. So this is a common data for following three questions. A differential amplifier shown below have some following specification, that is RC or identical resistors, that is RC1, RC2 both have 1.8 kilo ohm and RE resistor 4 kilo ohm, and supply voltage is 10 voltage and negative supply, positive supply plus 10 voltage, negative supply at the terminal, at the emitter terminal is minus 10 voltage. Beta value mentioned here is 100 and VB value is given 0.7. Okay, you can try this problem. So they asked you to calculate what is the value of resistance current. Resistance current are IE. That is emitter current IE. They asked you to calculate an emitter current IE. So from the derivation of the differential amplifier, can easily understand that 2IE is equal to formula I equal to V by R, Ohm's law, VEE minus VB divided by RE. So the value of VE is 10 and VB 0.7 and RE is 4 kilo ohms. So IE value is 9.3 milliamps divided by 8. So the answer is 1.16 milliamps. From the question, same. From the given data, they asked you to calculate what is the value of differential mode gain. Gain means output divided by input AD. Okay, output value divided by input value. So this is the output value divided by input value. And also a calculation of, see, AD is equal to output divided by input means output value of voltages is not mentioned in the question, and also we supposed to calculate that one. So instead of that, there is another way to calculate this AD by using the formula RC divided by RE. So in the introduction of a differential amplifier, we mentioned this one. AD is nothing but RC divided by RE. So RC is directly in the question. RC value is given that 1.8 kilo ohm, but the value of RE is not in the question. So we are going to calculate in the first step RE and then substituting that RE in AD. Okay. So RE value is what? Voltage, again resistance, Ohm's law, V by I, that is VT thermal voltage divided by IE. So VT value is equal to, what is the value of VT? 26 into 10 power minus 3, and IE value is, the previous step we got 1.16 milliamps, that you are substituting. Okay, the differential mode, the gain. See, if for AD we can use two sets of formula. One is out voltage, with respect to voltage means AD is nothing but output voltage divided by input voltage. But in the, instead of giving an voltage as a given data, they will give sometimes this resistance value. If resistance value is available in the question means you can use this AD formula with respect to resistance. So now in this case, in this situation, we are using RC divided by RE. Okay. So the value of AD gain is nothing but 80. So the next question in the same specification is, what is the output V0 if V1 is, what is the output format if the required voltage is V1 30 milliwatt and V2 is nothing but 40 millivolt. So what is the value of V0? So for this case, we can use a gain formula, that is the differential mode gain formula with respect to voltage, because here voltage is given in the given data. So based on the given data, we can choose the formula. So V0 divided by VD. So from this, by cross multiplying, you can get a formula for V0. V0 is equal to AD into VD. So VD is nothing but it is operating under differential mode, right? So differences of two input only we can able to feed. So differences of two input means V2 minus V1. So the V2, V1 values are given in the question itself. So directly you can substitute it 40 minus 30 milli volt. So 800 millivolt, or we can say it as a 0.8 volt. Okay. So the next diagram, that is the next question, is this one. Okay, this one. See the question. First, you identify what type of configuration is this. This is differential amplifier circuit diagram. In this, what type of configuration is? See the connection, only one input, so single input, dual output. In this case, the previous problem, dual input and balanced output. This problem is single input and balanced output. So this is the circuit diagram given. Here, this is an IE current is mentioned here, and this is your resistor value of RE, and this is RE, RE1 and RE2 of a transistor Q1 and Q2. This is RC1 and RC2 of transistor collector Q1 and Q2, and this is a source resistance. Here it is ground, there is no source resistance. So for this, the transistor will have a beta value of 100 and determine. So the question asked is, determine the input differential resistance RID. Okay, and then overall voltage gain. Voltage gain means output divided by input. So overall V0 divided by Vi is asked. And the worst case common mode rejection ratio, if common mode rejection ratio is going to calculate with some specific condition. That condition is mentioned here. If two collector resistance are accurate within plus or minus 1%. Okay, so the condition given here is supposed to calculate CMRR. Okay, if two collector resistance are accurate with 1%, so that condition we should apply in the problem. Each transistor is biased at the emitter current of 0.5 milliamps in the case of symmetric. Here it's feed with the non-symmetric, but results will be similar in both the cases. So first thing is to calculate the part of RE. First, RE1 and RE2 both are equal. So RE formula, the previous problem also the same thing we discussed. VT divided by IE. VT means 25 millivolt. Okay, IE value is nothing but a 0.5. Here it's mentioned in the question 0.5 milliamps. So totally the RE resistance value is 50 ohms. Input differential resistance is defined as, what is the value of RID? Is the formula of 2 beta plus 1 into RE plus RE. So the small RE is different and caps RE is different. That RE is nothing but here, and that is small case of RE is here. RE is 150 ohms. So totally we are getting RID is equal to this value. So the value of RID is nothing but 40, that is 40,400 ohms. That is written as 40.4 kilo ohms. So RS value is given in the question. From the diagram you can take this RS value as 10K here. Here RS value is 10K. So voltage gain from the input source, signal source to a base, that is Q1 and Q2, is nothing but VID divided by V1. The formula is this one, R by RID divided by RID plus RS. So you directly substitute the value of 40.4 resistance. So here we are getting right. So you substitute this plus the value of source resistance is from the diagram. We can take it as a 10K. So all values are in the K. Just cancel it, 0.8. We are getting the answer 0.8. So this is the value of RC 10K. You substitute here, and the calculated value here we are getting is 50. So what is the next value of AD? because we are going to calculate a common mode with a condition of has two collector resistance are accurate within 1%, right? So first we are calculating a gain, voltage gain, the differential mode gain AD. So AD formula output divided by input. So output divided by input is this one, but we are having a value of V naught divided by ID. So multiply and divide this value with ID here. So 50 and 0.8. So multiplied value is 40. So moving on to the CMRR, this is 20 log of AD divided by AC. That is the formula. So what is the value of AC here? Calculated value from the formula. It's a 50 into 10 power minus 4. While substituting this and then taking with the logarithmic, the value is that you are calculating CMRR with decibel level. So 98.06 dB. So the next question is, this is the diagram. So diagram is this. So from the diagram you can identify this is current mirror circuit. So here neglect all the base current and find out what is the output current I0 and I1, I2, I3. What is the output I0? When a base current is very less, this is equal to a reference current. That is the concept of current mirror, right? So from the current mirror diagram, that is R1, R2, R3, and this is your RS. From the diagram, the question asked is, so while neglecting all the base current, what happened? Beta of the transistors are very high. So first you apply KVL in the first transistor. The first transistor, first I0 you are going to calculate I1, I2 and I3, right? So I0, I1, I2, I3 are here. So we are going to calculate it. So before moving on to the derivation part, you convert this diagram. You just convert this diagram and then solve I0. So where is I0? So overall output value is I0, no? So for calculating the I0, we are applying for the first transistor KVL. So apply KVL. So voltage drop here is 6 minus I into R. Sum of each and every voltage drop across the branches is equal to 0. So that is a KVL, no? So 6 minus I0 into voltage into 10K minus 0.7 minus 1.4K I0 plus 6 is equal to 0. So you overall take this I0 in the left side. So remaining values calculated means the value we are getting is 1 milliamps. Since all the transistors are coupled to each other, the emitter voltages are same in the transistors as they are connected in parallel, because all the, see the diagram, all the transistors are connected in parallel case and all the transistors are identical in nature. That is, all the transistors are coupled with each other. So these are connected in a parallel combination. So what happened to your R not 1? R means V equal to I into R resistance through the resistance 1.4K here. Through the resistance 1.4K, here it is. Through the resistance 1.4, what is the value of voltage? So in the previous step, we calculated the value of I0. So you substitute here. The value of I0 you can substitute here. So overall value of V R0 is equal to R into that voltage is equal to Ohm's law. V is equal to I into R. I current value, the previous step we calculated 1 milliamps and 1.4K, the value is 1.4 voltage. Okay. So similarly, we can calculate the value of I1, I2. So VR2 is equal to I2 into R. The R value is 400 ohms. So that is the value of I2. I2 is equal to 3.5 milliamps. For the resistors of R3, what is the value of I2? Sorry, this is I3. It's not I2, it's I3. I1 value is this one. I2 value is this one. and I3 value is 1.4 divided by 500, it is 2.8 milliamps. Okay, so this is the next question. In an ideal differential amplifier shown in the figure, a large value of Re. So what type of configuration is this? This is differential amplifier with the dual input V1 and V2 and balanced output case. So consider these four options. Increase both the differential and common mode gain. Increase the common mode gain alone. Decrease the differential mode gain alone and decrease the common mode gain alone. So with general ideal differential amplifier, for a differential mode gain, the standard equation we already discussed is minus GMRC, and common mode gain, that is minus RC divided by 2RE. From this itself, we can easily judge that by increasing the emitter resistance value, okay, by increasing the emitter resistance, this one, by increasing the emitter resistance value, common mode gain will decrease. Okay, these are inversely proportional, right? A common mode gain and a resistor Re here. This Re is inversely proportional, so it will decrease. And the differential mode gain does not vary. Only common mode alone decrease. So the option is, from this we can say it is decreases the common mode gain alone. Why alone? It's only because only common mode is going to decrease and differential mode there is no changes. Why there is no changes means it is independent of your resistance Re. Only the Re resistance is dependent for your common mode gain. The dependency is also inversely proportional. So if the value of this Re is increases, what happen? Common mode gain will overall value will decrease. Okay, so it depends only on common mode, not depend on a differential mode. That dependency is also inversely proportional. So the answer is decreases the common mode gain only. Moving on to this question, this is your current mirror circuit again. Transistor M1 and M2 are connected with a current mirror. So what is the basic equation of I X is related to I bias? See, the current mirror, assume that M2 is saturated and the output is unloaded. And the output is here, it is unloaded with your load resistance. In the given circuit, from the diagram, we can easily say that the Ix value is equal to I bias. So I bias value is equal to Ix. In the current mirror circuit, in the theoretical section, we discussed that Ix, that is I output. Ix here it's mentioned as the output current. Ix current is the output current. When this Ix current is equal to an I reference, here the I bias is given as a I reference current. Okay, only the notations are different here. When this Ix will become an I reference, Ix is nothing but an output collector current, and I reference is nothing but a reference voltage. That reference voltage is equal to your output voltage. So that is the concept of current mirror, right? So when it both are equal means when your value of your base voltage is very less, that means which option is correct one? Both are equal. That is the reference voltage. That is the meaning of, that is the concept of reference voltage. That is the concept of current mirror. So the option B1 is correct because output voltage is equal to a reference voltage. Okay, these are all simple question. And moving on to the next current mirror. In the silicon BJT circuit shown below, assume that the emitter area of the transistor, that is Q1, is the half that of transistor Q2. Okay, this is the output current and here it's a reference current. What is the value of I naught? What is the value of output current? What is the value of output current? See, what is the value of output current? We should know what is the value of IA. IA is a reference current. So for each and every in different diagrams, they will mention the value of reference current. Our reference current is, what is the value of reference current here? Again, a Ohm's law, V by R. So what is the differences of voltage? 10 minus 0.7 divided by what is the resistance across it connected? 9.3K, right? 9.3 kilo ohm into 10 power 3. So the value of reference current IA is equal to 1 milliamps. So that 1 milliamps is flowing towards this loop. Okay, in this path, what is the current value is flowing? 1 milliamps. So I0 is equal to area of transistor Q2. I0 is collected at the collector of the transistor. This is the output current, right? I0, and this is the reference current. Here the reference current value is calculated. You know what is the value of IA? 1 milliamps. So 1 milliamps, that is area of transistor 1. Transistor 1, in transistor 1, the current reference current is flowing on, and transistor 2, the output current is flowing on. Okay. So imagine that the AQ2 is equal to what happened? It nothing but it's a twice the time of Q2. It's a twice the time of Q2. So we can frame this equation. AQ1 is equal to, that is AQ2 divided by 2. Okay, is nothing but I0 is equal to what happened? 2 milliamps. Is a twice the time, right? So I0 value is equal to twice the time of reference value. So output current is nothing but twice the value of reference current. So 2 milliamps we are getting for this question. Okay. Moving on to the next one, differential amplifier case. In the differential amplifier shown in the figure, the magnitude of the common mode and the differential mode gain are ACM and AD. If the resistance RE is increased, then what happened? Then what happened to your gain? AC will increase or AD will increase, or a common mode rejection ratio decreases or increases. So these are all the 4 options given. Whether common mode increase, that is common mode gain, or differential mode gain increase. Or another, what are the remaining 2 options given? Common mode rejection ratio increases or decreases. See, imagine this condition. Read this condition. If the resistance RE increases, what happen? The CMRR gain improves, right? It will improve. CMRR value will definitely improve when we increases the value of RE. So the option is common mode rejection ratio will increases when we increases the value of RE. Okay. See the next question. In the circuit diagram, the current I1 and I2 value is given. The transistor T1 and T2 are considered as identical transistors. Assume that the thermal voltage VT is 26 millivolt at 27 degrees Celsius. At 50 degrees Celsius, the value of voltages V12 is nothing but the differences of voltages is what? So that is, they are asking to calculate what is the value of V12. V12 is nothing but what? This is working under differential mode. So from the question, you can easily identify it is working under a differential mode. The differential mode of output is asked in the question. So this is the current I1 and I2. Okay, so we have a feedback here. This is a transistor T1 and a T2. So thermal voltages. Okay, thermal voltage of 26 millivolt at 27 degrees Celsius. But in the case of 50 degrees Celsius, what happened to your output current? So that is a question asked. From this, it is clearly understand that we are going to calculate a VT value in 50%, 50 degrees Celsius. So VT at 27 degrees Celsius is mentioned 26 millivolt. The first step is we are going to calculate again a VT in 50 degrees Celsius. In 50 degrees Celsius, what is the value of VT? So that calculation is the first step. So that the calculation part, we are getting that voltage is 27.844 millivolt. So how we are getting this? Moving on with the formula, we know that exponential format of current value for differential amplifier I is equal to I naught into e power v divided. This is a standard remember type of formula, neta vt minus 1. Okay, so I is equal to I naught e power v divided by neta divided by vt. So we know that the basic thermal voltage formula Vt is equal to temperature divided by 11600. So what happened to your temperature? Temperature is nothing but In terms of degrees Celsius, it is given 50 degrees Celsius. For 50 degrees Celsius, what is the value of VT? We are going to calculate. So this one is converted to a Kelvin mode. So degree Celsius is converted to Kelvin. We are going to add a degree Celsius temperature with 273 value. So 273 plus 50 degrees Celsius is converted as a 323 degree Kelvin. So what is the value of VT here? So VT is nothing but water. VT is equal to T divided by this value is the formula, no? So temperature here we are getting is in terms of Kelvin to 323. Okay, so the voltage of VT is 27. Okay, so the first step of calculation is over. So in the question they given that for this degree Celsius the VT value is 26 millivolt. The same VT value is calculated for 50 degrees Celsius is what happened? 27.844 millivolt. Then we are going to calculate the value of V12. So V12 formula is mentioned here. The current formula is standard. Remember type of formula is I naught e power V divided by neta Vt minus 1, and voltage formula is neta Vt ln of I1 divided by I2. Where here this neta value is not mentioned here means we can consider it as 1. If it is not given in the question, we can assume that value as a 1. So Vt value is for 50 degrees Celsius is mentioned here. We calculated in the first step 27.844. Okay, ln of L1, that is I1 and current and I2 current, both are mentioned in the question. So you can substitute 80 divided by 4. The value, last final answer we are getting here is 83.413. It's approximated to a 84. Okay. So the final question in the session is this one. The current mirror of figure is designed to provide IC current, the IC value 0.5 milliamps, and VCC total supply voltage given here is 10 volt and beta 125. What is the value of resistance? So here in the previous discussion problems, we calculated a reference current and then we calculated a output current I naught. But in this question, they given IC value. Okay, they given VCC value, but they are asking a resistance value in this case. So what is the output current here? It is IC. So what is the IB value? From this IC, we can easily identify because we know the formula IB is equal to IC divided by beta. From this, we can say that IB value is 4 microamps. Now the RER value is nothing but IC addition of collector current and a base current. So this is the value of 0.508 milliamps. So here VBE we can assume as 0.7. Okay, if it is not given, you can take it as a 0.7 or a 0.3 value for silicon and germanium. Therefore, the voltage drop in the resistor is nothing but 10 minus. What happened? Already 10 voltage is there. VCC already 10 voltage. Supply voltage is given as a 10 voltage, and 10 voltage minus the drop of your VBE, this voltage subtraction. Okay, 10 minus 0.7 is 9.3. So what is the resistance value here? R is equal to Ohm's law. Apply Ohm's law. R equal to V by I. So V value is here mentioned as drop up. Here is 9.3 voltage, and a current value here is because this is current of IR. That IR is nothing but what? Is an addition of collector current as well as a base current. So collector current is mentioned in the question, but IB value is not known. That's why in the first step we calculated this IB. Okay. Now you substitute the value. You are getting 18.307 kilo ohm. Okay. And this question, see this, in the current mirror this is a special case of current mirror, we are using this differential amplifier. This is somewhat a unique question. The circuit shown in the figure, you match the transistors with the thermal voltage VT. The base current of the transistors are negligible. The value of resistance R is K in kilo ohm, that is required to provide 1 milliamps bias current for the differential amplifier block shown. So what is your answer? So what is the value of resistance here, R? Same type of question like previous question. Here they asked an R value. Similarly, here they are again they are asking an R value, but IC1, IC2 values are given here, 1 milliamps and 1 microamps, and VT values here. What happened to your IB value here? In this case, in the previous problem, the IC values here, from that IB value we calculated, because we required a IB and IC value as a current flow for the resistor R. Here it is clean that IB value is 0. So no need to bother about the base current here. So what is the value of resistance? So we are going with a formula of VT divided by IC, ln of IC1 divided by IC, because based on the given data, you're supposed to change the formulas. Okay, so based on the given data, so based on the question asking, so you are just choosing a corresponding formulas. VT divided by IC1. So value of VT is given in the question, and IC1 is also, everything is mentioned. So just only substitution part is remaining. You substitute the value of resistance getting here is 172.7 kilo ohms. Okay, so far we discussed in this class differential amplifier basic concepts and basic derivations and modes of operation and different configurations, and then we discussed about the current mirror circuit and the current mirror circuit conditions and requirements, and then finally we discussed a previous year question papers of gate question in analog circuit, differential amplifiers and current mirror circuit concepts. Okay, so now we are winding up this class. Okay, thank you very much, ma.